Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we should finish this lecture right here. I just had a few slides to show you, and then we discuss performance at large scales, and in particular tail latency, which some of you have also already given some thoughts to. It's of course easier if there is a projection on the screen with the slides. All right, but before I continue, I have a question for you on the Clicker app. And here you go. What is the issue with assigning one task to each slot, as many tasks as slots? Is it that some tasks may take longer so that most slots will be idle waiting for the last ones to complete? Or there are no issues, this is the way to go? Or all slots are busy and not available for starting with the next phase, which leads to non-optimal performance? Or if a task fails, the whole Spark job fails, so a task should be assigned to 2 or 3 slots for fault tolerance. It's here, right? So let's look. Oh, wow. There is a majority, and the majority is correct. Congratulations. So yes, indeed, this is the reason. The problem with one task per slot is that the time that it takes to execute one task can vary a lot. And if you just assign one task per slot, then there are going to be slots that are finished very early and others that take longer. So if you have several tasks per slot, like 3 times as much or even more than that, 5 times, and you let the allocation happen dynamically, meaning that every time the slot is over, it just takes the next task, then this is going to go smoother, at least all the way to some scale. There's no issues, no, that's not correct. All slots are busy, no, that's totally fine that they're all busy. And remember that we said it's good to leave 1 core free or other things to give some to let the machine breathe a bit. And then if a task fails, the whole Spark job fails. No, that's not true. In fact, you just recompute, right? If you lose data, it might just that you might need to recompute more or less depending on what exactly you use, right? But it's resilience, and the original data is anyway stored somewhere, so you can always start again. Okay. All right. So then I move over to the slides. Here's a few slides that we have left on this one. And here you go. So data frames, this is where we left. I added this one just for today to remind you of what we saw in the data modeling lecture, why we have data frames. And again, the idea is when you have a collection of JSON objects, and this collection of JSON objects is valid against the schema, meaning all objects in that collection are valid against a specific schema, and that schema is closed enough, meaning that you don't have open objects allowing for arbitrary keys, you only have types that are instantiable and so on. There's a problem with the mic. Let me check that. Oh yeah, that might be that we didn't connect. Let me connect the mic and then you can hear us on Zoom. You heard me earlier, right? When I was closer to the computer on Zoom. Let's get reconfirmation. Yes, exactly. So I was just walking in the lecture hall and I was further away from the computer. But now I've connected the microphone, and normally you should be able to hear me fine now, right? Can you hear me on Zoom? Better, awesome, perfect. So thank you for letting me know. So the idea is that if the schema, let's say a JSON schema, doesn't have open object types, meaning that it says exactly there are these keys and exactly these keys
and all of the types are well defined. They are not abstract types, but really concrete types like integer, string, array of integers, array of objects with blah, blah, blah. Then you can actually visualize that collection of objects like is shown on the right as a data frame, right? It's basically a generalization of relational tables, except that now we can have nested values. Normally in a relational table, it's all flat. You cannot have nested arrays and objects, but in a data frame, you do allow nested arrays and objects, right? So it gives you this structure. It's still well structured, but a bit more general than tables. So the key thing to understand here is that a collection of valid JSON objects is a data frame. Who has the visual very clear in their minds of that? All right, so if I give you a collection of JSON objects and a schema, who would be able to draw this thing? Okay, many of you, awesome, perfect. So now it's quite easy to take it to Spark, because what happens is that if we didn't have data frames in Spark, we only have RDDs, then you can have, as you might remember, RDDs of anything. And in particular, you can have RDDs of JSON objects, right? And the way you would create the RDD of JSON objects, because Spark doesn't know about JSON, is that you first open a text as a text file, the JSON lines file with one JSON object per line. You open it as text. What you get when you open a text file in Spark is an RDD of strings, where every string is one line of the text, right? So you might get an RDD of 1 million strings. And then you use a map transformation, and you convert that to an RDD of JSON objects. What does the map transformation do? It just calls the parse JSON function on every string in the RDD, and it outputs a JSON object for each one of them, and then you have an RDD of JSON object. If you're in Python, it's an RDD of dictionaries, an RDD of dicts, right? For whom is that clear? Okay. The problem with that, you could do it. The problem with that is that it's not optimal, because these dicts, they all bear the keys of the object. So since it's all the same keys, but you repeat the keys in every dict, right? So it takes a lot of space in memory. It's not optimal at all. And the other thing is that to Spark, it's a black box. It doesn't know or treat JSON objects in any particular way. So there might be a lot of data that is totally useless, but Spark doesn't know that it can throw it away. So that's the second problem. So this is why we can work with data frames. And first, it's more convenient because you can take this JSON lines file and you directly get a data frame out of it. You don't even need to specify a schema because Spark will detect it automatically, right? It will automatically discover the schema and create your data frame. It's magic. It's just one line. You don't even need to parse JSON manually anymore. And then what happens is that you just call that view data set, for example, and that's then exposed to a table or what looks to a table in SQL. And then you apply SQL to the data frame, and then it's a SQL query there, right? And what happens is that it's more convenient. It takes less space in memory. And on top of that, it's able to figure out that it might throw away some of the data. In that case, you can't because there is a select star, but imagine that it's a select foo bar. Then Spark is able to throw away very early the columns that it doesn't need. And since data frames in the memory are stored columns by columns, it's very, very efficient to ignore some of the columns. For whom is that clear? Awesome. So this is what I told you yesterday. And this is extremely convenient. In fact, in the Jupyter Notebook and at the exam, it's even more convenient than that, because in Jupyter Notebook, you can directly write the SQL in a cell. You just need to write something like %% SQL or % Spark SQL, something like that, followed by the query, and it will just work. So in fact, the look and feel of using Spark SQL is exactly the same look and feel as using PostgreSQL. You just put your SQL query in your cell and it just works. So extremely convenient. If you don't like it, as I told you, you can also use the data frame API, not to be confused with the RDD API. It can be easy to confuse them, but this is different. That actually works on data frame. I have a preference for Spark SQL because since I already know SQL, it's easier to learn. The API, you need to understand what some things mean, like this ask, of theory, desk date. So you still need to learn a little bit how the API works, right? But again, you don't have to because Spark SQL works just as well. All right. And then to give you the intuition, we can open CSV, JSON, Parquet, and so on, and directly get data frames out of them, and it's automatically detected, right? So this is the idea. Do we have a question on Zoom? Can the data frame API also optimize Spark SQL? Yes, the data frame API is also able to optimize. In fact, from a performance perspective, it's the same. If you use the data frame API or Spark SQL, it has exactly the same effect. It's just that the Spark SQL language increases your productivity because you're going to be much faster writing a Spark SQL query than calling functions with the API. But from a performance perspective, this API is very efficient. And in fact, what happens, if I show you here, what happens is that there is this whole pipeline of optimization. You don't have to care about this. This is all happening automatically, but it's using all of the good old techniques from relational databases to optimize your SQL query or your data frame API query, and it's going to figure out the best way to execute it. So you will notice a very clear improvement in speed when you use data frames as opposed to RDDs. There's another question?
Yes, there is another question. It is related to the previous slide. Could you go back to the previous slide? It is, yes, on the slide where the question is, can we use limits in Spark SQL in the example dot take?
Yes, that's a very good question. And yes, you can use limits. So here I use take 10 instead. You could also have said order by target, blah, 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 limit 10, and that also works, right? In fact, in the latest versions of Spark, not only do you have limit, you also have offset. Remember, limit and offset from SQL? That's how you paginate the query results. So you have both limit and offsets, at least in the latest versions of Spark. And the nice thing about it is that it can also optimize that. Because if all you're doing is a projection and you have limit 10, it's only going to read what it needs from the underlying file, for example, Parquet or JSON. So yeah, absolutely, there is a limit. Okay. So these are the types that I told you about. This is a full table of types, but again, no surprise here. Again, no surprise. The only surprise is the map type, but this is not used so often. So you should really focus on array type and struct type. And in fact, you can declare schemas like that in Java or in Python. You can create, it's a bit involved, but you can create your own schema of data frames. And the idea is that it's mapped from this logical plan that you get from your data frame API. It's mapped to a physical plan, where in the end is going to be using RDDs, but in a very optimal way, right? And this is all the magic. So you see all the way from data frames and SQL, all the way to the right to RDDs, right? But now the RDDs are hidden. And now that actually also comes back to the question you asked. This is a fuller query where you have select from where, group by works as well, having order by, limit offsets. Now it's all supported in the latest Spark. And you probably now figured out that there's going to be shuffling for the group by and maybe shuffling for the order by. Why is there not going to be shuffling for the order by in that case? Yes? Exactly, we sort with the same key as for the group by, so we only need to shuffle once. But if it had been something different, then we would have needed to shuffle again. All right, very good. So this is it. And the good news is it's very similar to PostgreSQL, so there's not a lot to learn, right? Now there's a few more things than PostgreSQL, but very quickly I'm going to show you these more things. This is the same. Now, you know that data frames can have nestedness. Normally in a relational table, you don't have nestedness, but in a data frame, you can have nestedness. So it means concretely that you have a data frame here with first, last, and countries, arrays of strings. I could have drawn it nicely, you know, one per line. Here I just put the JSON array, but it's the same, right? So now I have an array of string. You agree it's not in the first normal form, right? Because these are not atomic values in here. So it's a data frame. And what we can do is in the SQL query, use the explode function. And the explode function is going to convert it in the first normal form in the way you see on the right. And what happens is that it duplicates the values of the other columns. Now it has one single value from the array of strings, but one single value for every record. For whom is that clear? All right, so this is what the explode function does. And I project to last And is it recursive? Well, if you want something recursive, it's more involved than that, and it looks like this. So this is equivalent. It does the same thing. It's called the lateral view. A lateral view, if you want to visualize that, is virtually you take that part that is nested and you expose it as a second table, as if it were a second table that you were joining against. And so that's called the lateral view. And so we say we explode countries as country, and that's an equivalent notation. But the nice thing is that then you can go recursive with this, right? You couldn't go recursive directly with this. You really need to use the lateral view. And here, if I use lateral view explode and then again lateral view explode, then I can have a cascade of normalization, right? You probably notice that it's becoming tougher to write, right? And in fact, it might give you a headache to understand what this is doing, right? For whom is that straightforward to look at this query and you know what it does? Not a lot of you, right? And for me, neither. It's not very straightforward. For some of you, maybe because that's simple enough, right? But imagine the same thing with, I don't know, 10 lines instead of just these, right? And the reason is we are pushing SQL to its limits here, because SQL normally is meant for tables. It's not meant for trees, right? So here we are pushing SQL to its limits. And we'll see in a few weeks that there are better languages to handle nestedness that are a bit easier than this, right? It is assuming that you have to know. There's a question.
It's assuming that you have to know the structure of the nested data to perform.
Yes, absolutely. You need to have information about the schema. In some cases, you don't have information about the schema. For example, I just gave you a data set without telling you what it looks like. And in fact, in that case, there is a full phase of schema discovery. You need to explore the data set in order to see what it looks like. And for this, languages like JSONic are more convenient than SQL in order to discover the schema of the data sets, right? But it's true here, to write this, you need to know about the schema. Okay. What about objects? If I have nested objects, well, what we do is we add dots to the SQL syntax. So then you can say name.first and name.last. It shouldn't surprise you if you're used to object-oriented programming, but we basically extend SQL with dots, right? So we add lateral views for arrays and dots for objects, and that kind of allows us to deal with arrays and objects, right? The problem is that first, it's complicated when you have to write queries like this, but there's an even worse problem. The even worse problem is that some of the data sets will not have JSON objects that follow the same schema, right? You might have a data set where on every line, foo is an integer, but on some of the lines, foo is an array of integers. That happens in real life. How do you do this? How do you build a data frame out of this? Well, you need to hit it with a hammer. You have no other choice. So if you hit the foo key hard enough with a hammer, you can actually squeeze it into a data frame. It's a bit forced. But what you actually did is that you created a colon foo of type string, and you just put there the serialization of whatever value there is. So in most cases, it's a serialization of an integer, and then you have the serialization of the array 3, 4. What happened here? We just push the burden to the user. Basically, what Spark does when it sees a file like that, it says, okay, fine. It's not consistent with the types. I'm going to make it a string. In other words, I'm making it your problem to deal with that. Because then you will have, as the user, to go through the values in here, maybe with the case statements, and then try to parse it again, because that's a string. So you need to parse it with your own code. And you need to switch and so on and so on. So you see, as a user, is going to be very involved, right? So these are the limitations of data frames and Spark SQL, and we'll solve them in a few weeks, right? It's important to know the limitations, because this is how you pick the right languages. So now you know in which case SQL is the perfect language. It's the perfect language if the data is flat. It also kind of works if there's a bit of arrays, but not too much. You can still manage objects too, but as soon as it's too much nesting and as soon as you have heterogeneity, then this is where it stops. This is then off limits for SQL. Who understands this? Right? Awesome. Okay. And you also have the flexibility in most APIs to go back and forth between data frames and RDDs, right? So if you have a data frame, you can force convert it to an RDD. And the other way around, you can take an RDD and convert it to a data frame if you supply the schema, right? When you do this, you have to help Spark a little bit, saying, take this RDD and convert it, and this is the schema that you should be using for that. Okay, that is the last slide, actually. I think this is pretty much it, okay? So you will have exercises. Spark SQL is part of the exam, right? So you will have practical queries with PostgreSQL, practical queries with PySpark, the RDD API, and practical queries with Spark SQL, right? Or the data frame API if you prefer. You have the choice. So that's already 3 practical elements of the exam. The 4th one will be JSONic, and that's it. And the rest will be theoretical. And you can exercise. We'll give you the data sets in advance ahead of the exam, so you can play on your laptops with the Jupyter notebooks. Okay. Great. We have questions. Yes, go ahead.
Is the schema related to Spark, or is it related to the type of data, like the data that you're collecting into the data frame?
Both. In fact, the schema, so when you have a data frame in the memory of Spark, then the schema is handled by the Spark code, right? So you have part of the Spark API is that you have a schema API, right? That allows you to go through a schema. What is important is that if you decide to save that data frame as, let's say, a Parquet file, what's going to happen is that the schema that was in the memory of Spark is converted to an equivalent Parquet schema. And the Parquet file contains the schema. In a Parquet file, you first have the schema, and then you have the actual objects, right? The actual records. So this is why it's both. The notion of a schema makes sense whenever there is a data frame, and that is true in the memory for Spark. That is true with Parquet. That is true with protocol buffers. That is true with Avro. There is another library by Apache that's called Arrow. Who heard of Arrow? Not a lot. Arrow is incredible because it's a way to literally copy over the memory bit by bit to the file and back. It's an extremely efficient way of saving a data frame to disk and loading back a data frame to memory. Really a bitwise copying. It takes the bits and pushes them over to the memory. Yeah. Did that answer your question? Not quite?
So could I just get XML schema, give it to Spark? Is it good?
No, this is not, for XML is different. So XML, this is the reason why actually I put more and more JSON into this. JSON maps in a good way to data frames. XML, it's more involved. So if you try to map XML to data frames, that's going to be more work, and this is beyond the scope of this lecture, right? So this is really meant for schemas. I could imagine that there are libraries that can convert between JSON schema and a data frame schema. But what you need to keep in mind is that whenever you have different technologies, there could be an impedance mismatch. So it might be that JSON schema has things that you cannot convert to a data frame schema, and vice versa, right? Does it make sense? Yeah, awesome. Any other questions? Yes, on Zoom?
Yeah, this is a similar question. The question is about why do we need the schema when convert to data frame from RDD, but when parsing JSON, we don't need a schema.
I actually don't know, because they could actually have also added a way to not provide the schema when you convert from an RDD and to infer it. Maybe in the future, they will do this. I think it's really a design choice that maybe it's because it might be easier to do in the case of a JSON file, but I really don't have an answer. There is at least no technical limitation why this is not possible. It's just that the API right now requires a schema, right? Does it help? I assume yes. Yes. Okay. And can we supply? There's another question.
Yeah, the question is, can we supply a schema when parsing JSON into a data frame to avoid inference?
Yes, absolutely, you can. The API allows you to specify the schema, And in that case, it's going to be faster, right? Because if you already have the schema, then you don't need to discover it. So it's going to be faster. So in some cases, you do have it, and then you supply it to Spark, and it's almost instant. No more questions? Okay. Well, you will have the exercises to exercise with this. You're welcome. And we'll continue with collections of trees. We'll look at document stores. Probably next week we'll start. And then we will look into the JSONic language. So we'll continue to work with these things. Okay, so then I shall move over to the next part.